this computer, and we are recording right now. Thank you. I'm going to share my screen, and we're going to jump into a couple of concepts here tonight, make that as big as I can. And there we go. All right. So if you're taking notes tonight, this is chapter 14, all about arithmetic and geometric sequences. A sequence. Okay. A, B, C, D, E, F, G. That's a sequence of letters. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a sequence of numbers. Okay. So when they talk about a sequence, they're talking about a row or a list of numbers that are in some kind of a sequence. So that's what a sequence is, just by definition. Okay, it's a row of numbers. And sequentially, let's see here. Do I need to, yep, I need to unplug my videos. Sorry. Well, you guys are copying. I am plugging things in over here. Okay. So we got this thing called a arithmetic sequence in mathematics. And in an arithmetic sequence, the next number in the sequence is found by adding the same number, okay, to the previous one. So if you were taking abbreviated notes, if you just copy down the words I underlined in an arithmetic sequence, next number found by adding the same number to the previous one. So these are examples of arithmetic sequences. You have 2, 4, 6, 8, 10, 12. We're adding 2 each time. Okay. Another example, just to kind of familiarize yourself with, if I had -8, that's like way to the on my number line. Okay, if this is 0, okay, that's way out here at -8. Okay, if I added 3 to that, it's going to get closer to 0. It's getting greater, so it would be -5. If I added 3 to that, it becomes -2. And then if I add 3 to -2, it becomes 1. Okay, a positive 1. 1, 2, 3. Okay. And 3 to that, it becomes 4. And 3 to that, it becomes 7. Okay. So just knowing that sometimes you're starting with negative numbers, and they're getting bigger because they're getting larger. -5 is larger, greater than -8. Okay. And then in this case, the last example, I am adding -2, or it's the same thing as subtracting 2 each time, but it's like you're adding -2. So 7 plus -2 is 5, plus -2 is 3, et cetera, et cetera, et cetera. Okay. So the key concept on this page is what I underline in red, that an arithmetic sequence, and then maybe at least copy down one example. Okay. And it's the same change each time. That's going up by 2, going down by 3 each time, going down by 2 in this case. Okay, it's the same each time. We're adding the same number, a 2, a 3, and a -2 each time. That's called an arithmetic sequence. Okay. By the way, well, let me see if I get into it in a moment here. Okay. All right. Yeah, this is the one. This will be the slide. All right. Excuse me. Give you a few moments to copy down what you see on the screen here, especially, well, especially the idea of this n term. The key concept on this page is this thing called n, okay? What term we're talking about. So I will tell you that we're going to be a little bit rushed tonight to get through both chapters, but we'll make it. All right. In this sequence here of the sequence of 2, 4, 6, 8, 10. Remember that from the previous slide? Okay, we're going up by 2. It's the same change each time, okay? The first number, 2, is called the first term, okay? So that's why I put a 1 above it and then a 2 above the next and a 3, etc. Okay? So in this sequence, this is term 1, okay? This is term 2. I'm going to get better at writing with this pen one of these days. And this is term 3. So I wanted you to get used to this idea that you can label each of the terms in a sequence, like term 1, term 2, term 3, okay? Um, likewise, you don't have to copy down my chart over here on the right, but it's another example. If the first term was 1, you know, the y and a y value is 2, the first term is the first x value is 1, the second term is 2, the third term is 3, etc. Of the x values. And when we're talking about x's and y's, this is the x-axis, this is the y-axis. Here's all my x values, okay? All right. All right, so anyway, so we have what we call a sequence here, an arithmetic sequence, okay, where you add the same number each time. Now, there's a formula, which I want you all to copy down, for an arithmetic sequence. A formula is a way to calculate whichever term we're trying to figure out in that sequence. And so I want you to copy this down carefully, and you will get to use this same formula on your homework that you're copying down. You'll also get to use it. I'll let you use your notes on the third exam in my class coming up next week. So in an arithmetic sequence, the formula is n. Okay, this n here stands for which term am I talking about? The first one, the second one, the third one, the fourth term. I can figure out whatever term I'm trying to find out by using this formula right here. Starting value, okay, plus, okay, plus, and then in parentheses I've got here n minus 1, okay. N means the term I'm trying to find out, okay? The term that I'm asking for, minus 1, okay? Times the number we're adding each time, the added number, okay? So that's my formula, starting value plus, and then in parentheses, n minus 1 times whatever number I'm adding each time. Okay, so, all right, let me guide you through this. If I applied this, if somebody told you in this arithmetic sequence here of 2, 4, 6, 8, and 10, find the fourth term using the arithmetic formula, the arithmetic sequence formula.
8 and 4.
Yeah. So I've got, you know, but let's say I didn't know it was an 8. Let's say they gave you, listen to this, if they gave you the first 3 terms and they didn't tell you any of the rest of the terms. And
But
they
it's
said,
by 2s, you can tell.
yeah, well, in this case we can, but sometimes it'll be a lot more complicated. So that's why we got to use this formula, okay? Like for instance, I'll give you an example. And they use this in banking. They might give you a certain amount of terms, but find the 27th term, okay? Rather than having to try to like add it up all the way up to 27, especially if it was changed by 17 each time, okay? You could apply the formula and figure it out way faster, okay? So if they wanted this fourth term here, here's what watch how it applies to this example here. Starting value, here's my starting value right here is a 2. So 2 plus, all right, the n is the term we're trying to find out. The n You see how it was n minus 1? We're trying to find the fourth term. So we put that right in parentheses. Here's the 4 right here. We're trying to find the fourth term. Minus 1 times, we figured out that we're changing 2 each time. Okay, so times 2. That is the added number we're timesing. Okay, so watch how I do the math. There's the numbers now. 4 minus 1 is 3. Times 2 is 6. Plus 2 is 8. Okay. So I figured out what the fourth term is. Okay. This n, in this case here, I'll call this n4 here if I want to over here, term number 4, by applying that formula to it. And again, the n is which term we're talking about, like on this list of terms here. Is it the first, second, third, fourth, etc.? Okay. That is the arithmetic sequence formula. And again, arithmetic sequence means we're adding the same number each time. It changes the same each time. All right, I'm going to move on. Okay, this is the same thing here. Okay, so basically, maybe don't worry about copying this down here. Okay, but let's just follow along the logic here. Okay. Let's say that I had a sequence that was 7, 10, 13, 16, 19, but I didn't know what my last few terms were, okay? But I figured out in this is a sequence that's going up 3 each time. You can see it. 7 plus 3 is 10, 10 plus 3 is 13, etc. Okay, and this is my first term, okay, is the 7. My second term, or term 2, my n2 is 10, my n3, term 3 is 13, my n4 is 16, etc. All right. So if they ask you to find, they said, all right, find the fifth term in this sequence. And again, I'll remind you, they might ask you to find the 12th term, okay? And that'd be way out here somewhere. We could go, okay, here's our formula. It's over here again. I put it again on the page here. N equals whatever term we're trying to find, the start value. Okay, that's this first number here, 7. Where did I get that? From right here. It's my starting value in the sequence. It's my first value. Plus, now, we're asking for the fifth term. So in this case, n is a 5. We plug the n in here as the 5. That's the term we're looking for. Minus 1 times, how much is it changing each time? By 3. That is the added number each time is 3. So I'm going to now cross this out here so it just doesn't confuse me. 5 minus 1 is 4 times 3 is 12. Okay. Plus 7 is 19. Okay. Could you find the 12th term in this process without, they only gave you the first 5? You would go starting value plus 12 is now my n. That's the term we're trying to find. That's the n, they're calling it, minus 1 times 3. That's 11 times 3 is 33, plus 7 is 7, 8, 9, 10, 40. Okay, so bankers and investors use formulas like this to calculate out way out into the future something. So they'll know how long it's going to take us before we're making a profit on something. Okay, but that's an arithmetic sequence. All right, next slide. I'm going to pause this for a little bit, give you some time to copy down something called a geometric sequence. And that is the next term is found by multiplying the previous number by the same term. Okay. I'll let you copy that down and I'll guide you through this. Okay, I'm going to talk about what's on the screen here. So we've got a sequence of numbers. This is the actual sequence right here. 3, 9, 27, 71. Okay. How did I get from 3 to 9? 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 71. Okay. So what we're calling the multiplier, and again, this is what we're doing. We're multiplying now. We're not adding. Okay, we're multiplying. That's the key concept. You know that you're talking about a geometric sequence here when we're multiplying. 3 times the previous term. 3 times 3 is 9. 9 times 3 is 27. Okay, so that's what we call a geometric sequence. And you'll notice, by the way, that it goes up way faster when you start multiplying things. You know, it's not just 3, 6, or 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. By the time we got to our fourth term, it would have been 15 if it was a arithmetic sequence, but we're at 71 because we're multiplying, okay? So that is an example of a geometric sequence. In the next example, my example 2 here, okay, here's my actual sequence of numbers, okay? And again, just to keep reinforcing this for you guys, term 1 is 2, term 2 is 4, term 3 is 8, etc. All right, 2 times 2 is 4, 4 times 2 is 8. It looks like the multiplier is 2. I'm multiplying each term times 2 to get the next term. And it's the same multiplier each time. So, excuse me, so it is considered a geometric sequence. Now, for your homework's sake, once in a while, they'll throw in a sequence of numbers and they'll say this: is this an arithmetic sequence, geometric sequence, or none of the above? And if you are going along and all of a sudden it's the multiplier of 3, but then all of a sudden you get another number that's different than 3 times 8 or 3 times the previous term, or in this case 2, but I'm looking at the first example of 3. If you start getting a different number that's next, and it's not arithmetic sequence, and it's not geometric, it's not the same multiplier, then you would say none of the above, or it's none, it's not geometric or arithmetic. Okay, so again, the key concept: a geometric sequence is where you're multiplying the previous term by the same number. Arithmetic sequence, you're adding the previous term. Okay, all right. Now, just like arithmetic sequence has a formula, okay, you're going to add this to your notes. Geometric sequences also have a formula that's, well, it's just slightly different, okay? So you got this geometric sequence formula, and key thing is I want you to be sure and copy down what I'm just putting in the box here. Okay. That's our little magic formula, and I'll walk you through this, okay? For figuring out the nth term, whether it's the 7th term or the 15th term, the n is which term we're trying to find out, okay? That's why they use an n there. It's kind of the symbol they use for term here, okay? N means the term, which one? So, all right, I've got whatever term I'm trying to find out in a geometric sequence. I start with my start value, okay? This is the word value here, okay? Times, oh, this is from the last slide when he said times. When I'm timesing the same number, it's geometric, okay? In parentheses, the multiplier. What's the multiplier? That number that we're timesing each time. Like the first example was times 3 each time. The second example, it was times 2 each time, okay? That's the multiplier in parentheses. And then this right here, this n, the n minus 1, is an exponent. like 3 to the third, okay? It's the exponent, okay? And that changes things much more rapidly, okay? So, but that's the kind of the magic formula. So I'm going to walk you through that with an example here, real slowly here, because I want you all to feel like, okay, I think I'm seeing what he's doing there each step at it along the way. All right, there's the formula. Let's look at my example here. All right, in my example, I've got a sequence of numbers, okay? 2, 4, 8, 16, 32. I'm going to think this through. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is my multiplier, okay, is 2. That's the thing I'm multiplying each previous term by, okay? If I was labeling my terms, again, this is term 1, 2, 3, 4, and 5, the fifth term. All right. Now, in my example, let's say, that's why I have this arrow here. Let's say that I didn't know what the third term was here, okay? And let's say they said, all right, use the geometric sequence formula to find the third term in this sequence. Let's say you didn't know, because like I said, they could be asking, find the 30th term in the sequence, all right? That'd take a long time to do that all by hand, figure it out. Let's put it in our formula. Starting value, okay? There it is. My first number is 2 times, okay? What was my, it says the multiplier. What's my multiplier? It's 2. To the, this is the exponent, okay? It said the n you're looking for, this n right here, minus 1. My n was 3. We're looking for the third term. All right, so I'm going to walk this through. What is 3 minus 2? I'm sorry, 3 minus 1. Okay, 3 minus 1 is 2. So this is now 2 squared. Okay, 2 squared, again, look at this 3, the n here, the n is 3. That's the third term we're looking for, is this third term here. 3 minus 1 is 2. So this becomes 2 squared. 2 squared is 4 times the starting value is 8. And sure enough, it's the third term. Now again, that's easy to figure out right here because we've only got 5 of them. But what if they said find the 12th or the 15th term? Here's what we would do. The n up here, you see my little green dot moving, that would be, if let's say it's the 15th term, this would be 15 minus 1, which would be 15, it would be to the 14th, okay? Which, by the way, I need to show you how to do in a moment on your calculator. In fact, if you have your calculator handy, I will just tell you, I'll draw it. I think I have it on one of the next slides, so I'll hang in here. Okay. All right. This one here, I don't want you to try to copy down. I just want you to look at it and just listen along with me and follow my logic as I talk through this. Okay. This is example 2. Okay. And again, I will send this slideshow to you in email tonight. So you'll have this, plus you'll have the recording. Okay. All right. I've got a sequence of numbers here. Here is my sequence. I have 5 terms here. 5 times 3 is 15. 15 times 3 is 45. 45 times 3 is 135. It looks like I got a multiplier of 3. Okay. All right. So let's say that I'm looking for, they say, find, and I didn't know it here. Okay. In this case, just find the 4th term in this geometric sequence. I'm going to plug it into my formula. Starting value, n, the n4, the 4th term would be starting value right here, 5 times, you guys remember when you have numbers right next to each other in parentheses like this, it means times, times The multiplier, which we determined was 3 here, to the n minus 1. So what's the n here? Well, we're looking for the fourth term. This would be 4 minus 1. Because we're looking for the fourth term, okay? So that's what that n is, okay? Term number 4. Okay. So then what I'm going to do is 4 minus 1 is 3. So now this becomes 3 to the third. 3 times 3 times 3 is 27. 3 to the third equals 27 here. 5 times 27 is 135. Okay. So the fourth term, n number 4 here, like if n4 is 135. I can use as a banker or an investor this same exact formula, and I could figure out, let's say these numbers here were what I'm advancing after each quarter or each year or something. I can predict out 15 years, 15 quarters, 15 terms in a row, and see how much money I'm going to have in 15 years in this investment. Okay. If it's geometric, if I'm multiplying by the same amount each time, like when we were talking about percentages, like if you had a 20% growth each year, okay, we can now take the results of 1 year, multiply it by 20%, and we can go and figure out using this formula, okay, because here's now my multiplier. This would be my multiplier if it was a 20% growth each year. I can use this formula and calculate out in 10, 20, 30, 50 years how much money I'm going to have in my savings account or my CD, my Roth IRA, or whatever the investment I'm making using this kind of math. You see why it really does apply to the real world. Okay. Okay. This is kind of like a change of topics for just a couple of minutes here. So I'll give you a moment to copy down what's on the slide. I hope you guys are doing okay. Kind of have a lot of stuff tonight, and I might give you like I don't know, a minute break here after we finish this chapter to stand up, grab a snack or something. Let me talk a little bit about what's going on this slide. And again, being also an English teacher, I always try to think of ways to remember words because I teach a lot of vocabulary. You guys see the word deductive, okay? That's got the word D in it, the letter D in it. It's like going down, okay? If you want to add that to your notes here. When you're using deductive reasoning, you start with a general principle here, okay? Like I've got my general principle here on my slide here. I got a general principle, a big idea, okay? You can think about this as the big idea here, okay? All right, I've got a big idea. And in deductive reasoning, we kind of come up with a big idea. And then from that, we move down to the specifics, specific examples and incidences. It's called deductive reasoning. You start with a general theory or idea, and then you move down to the specifics. All right. In inductive reasoning, okay, in a sense, in my little diagram here, it's like I'm going up. I'm starting, like it says in my definition, I start from the specific facts. Okay, you can think about these little facts on the ground here. If this is the ground, okay, I'm a scientist looking at all the facts going on the ground here, and I got all this litter on the ground, and so I'm going to induce that a big theory that, you know what, if there's all this litter here, there must be people around, or people must be camping nearby or something. I'm coming up with a general hypothesis by looking at the small details first and moving up to that's inductive to a theory. Okay. Whereas in deductive reasoning, we think of a big idea and then we move down to the specifics from that. So simplest way to remember this, guys, deductive versus inductive, is this letter right here, D. Think of D as moving from a big idea to down. In your notes, have kind of a big idea at the top, okay, moves down to the specifics. So in the textbook, that's a better explanation. I mean, I just gave you a better explanation of deductive versus inductive reasoning. The slight difference. Okay. All right. I'm going to move forward here. Hey, it's time for our 60-second break, guys. Let's just do this. Let's take a minute and a half. I don't know. Yeah, and do I have the ability to stop this recording? Pause. Okay, guys. I hope I gave you enough time to stretch your legs and kind of maybe rub your temple of your head, give yourself a head massage, and maybe grab a snack. So we're going to jump into the very last chapter of the whole quarter. Yay, this is it. And once again, while you're copying this down, maybe you can write and listen. You will get this slideshow in email tonight. So if you wanted more time to write some things down, you'll have that. And number two, you are also going to have the video, which will be a little bit longer video because it's just both two long, kind of complex chapters. I'll put it on YouTube. I'll send you the link if you needed to listen to it, and you can put it on fast forward so you can listen to it a little bit faster like this. So I talk a little bit faster, but maybe you can go to the place where you need and then listen a little bit more slowly. And then just as an announcement, of course, this is the last full week of the quarter. There is a final exam next week. Here's what I'm going to do, because we don't have enough Tuesday nights. Next Tuesday night, we're actually going to have a class, okay? And I will go over the everything that's going to be on exam number 3. We're calling it the final exam. It'll be just based upon chapters 1.11 or chapter 11 through 15, basically, okay? And I also should remind you guys that your WAMAP homework is all due next week as well, like Tuesday or Wednesday. So be sure that if you've kind of neglected that you spend some time this weekend catching up on some WAMAP homework. And then please listen to this announcement very carefully. Do not do chapter 15 in WAMAP, only in WAMAP. You do 15 in the book homework, but in your WAMAP homework, there's no chapter. There is a chapter 15 in WAMAP, but I don't want you to do it. I'm not going to count that against you. So WAMAP through chapter 14 and you're done. Okay, so this slide's a little bit of a review of some things we have talked about so far in this class. You've got independent variables, and if you have a science class, okay, something called an independent variable, okay. It's the input typically on a chart. And an example could be hours worked, or it's also considered the X. So if I'm charting something and I was charting grades, okay, and these are my X values down here. Remember the X axis and the Y axis. This is the X values, okay? And then I said, they've done some research and they found that for every hour you study, it affects your grade, okay? And actually, they have done studies on this, and you can study too much, and it actually starts having a little bit of a diminished effect on your grade. But in this example, okay, the X value, this is an independent variable because how many hours I study, I'm controlling that. Okay, I'm giving that input into it. Okay, I'm going to put 3 hours of study into my final exam for Tim's 76 class. Okay, I'm controlling that. That's called the independent variable. Nothing's affecting that except for my decision to do that many hours of studying. Okay, all right, the dependent variable is the output. It's what is the result. This is another word. You could actually write the word result. Okay. Um, it is the result of how many hours I study. Okay. It is the result in a science class of how much sunlight the plants get. 1 hour, 2 hours, 3 hours of sunlight affecting growth. So the dependent variable might be growth in a science experiment. The independent variable might be how much sun they get. I'm controlling that. Okay. Now, in this chapter, they will also start calling it a function. This word function down here, it is kind of like the same thing as a result of the X value, which means how much growth, if I was charting this on the chart, how much growth, let's say it was directly in correlation to the how many hours of sunlight. If this was sunlight here, okay, and 1 hour is 2 hours to 5 hours. If for every hour of sun you give this plant, it really likes sunshine, it grows, an extra so many inches after a month or something, so many inches a month. So if each day you give a plant 3 hours of sunlight, it gets to this point right here. And each day that you give it 5 hours of sunlight, it grows this much, okay? So the amount of growth is a direct function or result of the X value, okay? And so that's why they're calling it a dependent variable. It depends, how much my plant grows depends on how many hours of sunlight I give it. What kind of grade I get depends on how many hours of study I put into my studying for my final exam. So those are the different kinds of variables. And that's a review. We went over this about 2 or 3 weeks ago. Okay. All right. So that being said, I do want you to go ahead and copy down just the picture of linear growth. Okay. What it looks like, and linear decay. Most of the time, we're going to be talking about linear growth in a science experiment, but not always. So I'm going to give you a moment here to copy down what you see on the screen here. Give you about 30 seconds. Can you hear my dog barking in the background? Yeah. Yeah. She's a little Napoleon. She thinks she's the boss. I don't know what it is about little dogs. When they see big animals, they bark at them. You'd think they go, I'm going to keep quiet here. But no, little dogs, they see a big dog, they're going to start barking. It's crazy, isn't it? Okay, so back to math here. Talk about linear growth. Linear growth. Okay, I want you to take your pen, your highlighter, and you see this word line here. Okay, when you see growth that's in a straight line like this, that's called linear growth, okay? And it's taken straight from, just like those pie charts is like a pie, and a bar graph is like, has bars on it. Linear growth has line, it's a line, okay? So it's growth in a line, either up or decay is down, okay? But if you see a line, you know it's a linear growth, okay? And likewise, just like in the last chapter, we had arithmetic function and a geometric function. We're kind of exposing you to what they call the linear function, which now we're applying it to a graph here, okay? And so you see this y here. I'm going to change colors here just to illustrate here. See this y down here in the bottom left corner here? The y, if you're trying to figure out what the y is, okay, and this was grades, or this is pay, how much pay you make based upon how many hours you work, okay? The y, you can calculate the y, which is growth of a plant, how much money you're making, what your grades are going to be, any kind of thing, based upon the x value, okay? This is x1, 2, 3, 4, etc. Okay. So if I wanted to figure out something way up on my chart here, 30 numbers up, I can figure out the y on a linear function, a line function, if it's linear, by starting very similar to the last chapter with the starting value, okay, plus, so this, you'll see this is very similar to the arithmetic sequence, okay, plus the rate of change, okay. So is it going up by 2 each time? Is it going up by 3 each time? Are we adding -3 each time? Okay. So plus the rate of change, okay, times, this is the times symbol, okay, times the independent variable, which means the x value, okay, which we'll get in a second. So I take my red pen and I circle, I can figure out the y value, okay? I can figure out one of these y values here by using, no matter where I'm going to try to find it, by whichever y I'm trying to find, by going with the starting value, okay? The starting value, okay, that they give me, plus the rate it changes 2 times each time or 3 times each time, okay? Times whatever number I am on this X line here, the fourth one or the fifth one or whatever. I can use that number and figure out where I am on this Y value, on this Y line here, okay? So I'm basically in this kind of growth, we're trying to calculate the Y. We're trying to find out the dependent variable, okay? The one that's a result. All right, let's take a look at an example here, okay, to illustrate what we just talked about. And I will give you a, you know, all right, give you a moment here to copy this down here. Because now they're going to start putting things into charts as we get into, some of you may remember this from previously in basic algebra. They'll start the X and the Y. You see, I want to really make sure you're correlating here. This X is, what are we talking about here? Which number on this X axis here, okay? And the Y, we're talking about, where are we on the Y axis, okay? That's what it's really mean. What is the result? What is the dependent? I'll put DEP here for the dependent variable. And this is the independent, IND, it's independent. The X value is independent, okay? All right. So we got a chart, okay? X0, okay, is minus, that's my starting value, is minus 18, okay? After 1 quarter, okay, I'm at minus 12. After 2 quarters or 2 years or whatever it is, or the third term or the third X value, it's 0. So it looks like I'm adding, if I start with my starting value, negative 18, and I add 6 to it, remember the number line, this is 0. Negative 18 is way out here somewhere, okay? If I add 6 to it, I'm going to get to negative 12. Okay, I'm moving closer to 0. Okay, if I add 6 to negative 12, I get minus negative 6 because I'm getting closer to 0. If I add 6 to negative 6, I get 0. Add 6 to 0, I get 6. My rate of change is 6. It's a positive 6. Okay, I'm adding 6 to it each time. So it's actually getting bigger each time, even though these numbers look like they're going down. Don't be fooled by that. It's actually getting greater because 6 is a lot greater than negative 18. Okay. All right, and then this is like which term it is. Okay, so my starting value is negative 18. All right, if I wanted to find out, put this in the formula, okay, the y, okay, so because this might be way down here. I'm continuing my chart here. I should go to the same color here. If I'm continuing my chart here for my y values, I might be way down here, trying to chart one of these y's, okay, which y it is. Starting value, here's the formula. Starting value is negative 18. Okay, there it is right there. I'm going to draw a line to it. There's my starting value. Plus, that's the formula. The rate of change was 6 times, now, the independent variable is the x. Which one is it? Is it 1, 2, 3, 4, 5, 6? Okay, whatever. Now that x value, I've put it in the chart here, 0, 1, 2, 3, 4. So that's the x value. So if it was the third term, then I would pick this 3 here, times 3, okay? That is the formula for calculating what we're calling here, if I go back in a slide, just to illustrate, linear growth, because it's in a line and it would give us linear growth. It's the same, the rate of change is 6 each time. We're adding, see that plus sign there? That's linear. See that plus sign here? That means it's like an arithmetic growth, okay? All right. I'm going to move on to the next slide here. And I should tell you, I'm sorry that it seems like, hey, this is like a lot of concepts. Yeah, it's 2 chapters and they're kind of the last 2. Okay. So here is an illustration of what we just talked about. So you don't have to copy everything down here. Probably the most important thing you might consider copying down is over here to the right here, my little post-it note here. If you're adding or subtracting, it's a linear growth pattern. If it's the same number that we're adding each time, it's linear, okay? If you're multiplying, it's exponential, just like when you were multiplying, it was geometric, okay? So here's my illustration here, okay? My x values is months, okay? So if this was my chart, this is my x value, month 0 is right here. That's my starting value, okay? I started with $800, okay? That's ahead 0. And then after 1 month, I had 750, okay? Two months, I had 700. 3 months, 650, okay? In this chart, this is the month, okay, and then is the x value, and that's the independent variable, okay, 0, 1, 2, 3. And the y value is how much I have to pay off on my loan here, or how my bill I have, my Visa bill or whatever, okay? But look at my y values. I'm noticing that it's going down 50 each time. 850 minus 50 is 750. 750 minus 50 is 700, etc. Okay. So I can figure out, I can use my formula and start with my starting value. Okay, I'm going to draw a bright yellow line here. Starting value, here's my starting value right here. Okay, plug it into my formula. There it is, $800. Minus, now the reason I said minus here instead of plus, because we see we're subtracting 50 each time. You see that? So that's where that minus came from instead of a plus. The rate of change, we already looked at the chart and we said, oh, it's changing 50 each time, okay? And times, let's say that they wanted us to find the third term here after 3 months, how much I would owe on Visa bill, paying $50 each month. That is now my independent variable. Is my X is 3, okay, the third month. So you'll typically, that's the kind of problem you'll see is something like this. And all right, so this is linear growth. All right, let's go on now and talk about geometric. Now again, line, linear, it's in a line, and we're adding or subtracting the same amount each time. We're adding, it's plus or it's minus, the same amount each time, okay? We're not multiplying, okay? So this is linear growth. Let's move on to geometric, okay? All right, excuse me, exponential growth. All right, gonna give you give you guys a minute or so to just relax and copy down what you see on the slide here. We're almost done. This is it. This is the last concept of the whole course. Geometric, and then exponential growth. I should tell you, as a little real world application, that there's a guy by the name of Dave Ramsey who's written books and has videos out on YouTube. He'll show you how to be a millionaire, even if you have just an average job. I mean, you just make middle, even to lower average wages. I don't know, whatever that would be, but after so many years, he'll show you how you can have millions. You can reach your first million, and etc. And he'll use this formula. This is what investors use to calculate exponential growth, where you're multiplying each time. Okay. So in exponential growth, we have you're going to increase or decrease by a constant multiplier. Okay, that multiplier becomes really powerful, okay? As the inputs x increase by 1. And inputs are the x value on that x-axis, okay? Now, one key thing to look at is to be able to just identify the difference between linear growth and exponential growth. Exponential growth, here, if I change to red here on this thing, you start off maybe not seeing a whole bunch of growth, but then you start making a little bit of growth, but you keep multiplying what you made last year times new, and pretty soon you start making big bucks at some point you start really making money, because now you're making 20% interest each year, and you're adding that to the year before, and you're multiplying it, and you're multiplying that 20%. So exponential growth looks literally like this physically on a chart. It looks like this, okay? Or if we're saying exponential decay, let's say the economy was going downhill or something, it looks like that, and it is really going down fast at some point, okay? So again, to review, if I see on a chart growth that looks like this, it's in a line, it's linear, it's got the word line in it. If I see growth that looks like this, that's what exponential growth looks like. All right. Likewise, there's a function, which I'm now calling a formula, or they call it a function, but I put in parentheses the word formula, because maybe that means a little bit more to you. They call it the function of the y value for exponential growth. I can figure out my y value. Okay, this is my y. I can figure it out 20 years from now, 30 years from now, using my exponential growth formula. This is why, for instance, if you ever thought about how much money somebody who owns an apartment complex makes, maybe somebody in the classroom has thought about this. Okay, yeah, it's look at all these renters, and they're all paying $1,000 or $1,200 a month, or 2,000 or whatever it is a month, and there's 50 or 100 units, and each one of them is paying $2,000 a month or something. That's a lot of money coming in, right? But before you get too greedy, you have to think of how many millions of dollars did it cost them to build that apartment complex, plus, of course, maintenance and paying people to work there and stuff, it costs millions up front. So what happens is investor groups, like groups of investors who work, they will join together and put in the $1 million, a couple $1 million to build your apartment complex. They're losing a lot of money at first. They're putting a lot of money into it. Then they have to hire people and train people, and they have to all the insurance they have to set up and the lawyers they have to hire. Millions of dollars in the hole. Most of us can't do that. But here's what the investor group's thinking. They're going to use this if we are growing exponentially, which means we have exponential growth. This Y down here in the bottom left-hand corner, we can figure out after so many years how much money we'll have coming in, which means we've paid off the millions of dollars to build the apartment complex. And at some point, once that building's paid off, whether it's 10, 20 years in the future, then your investors are making big bucks off from your apartment rent. Okay. Um, and I can just tell you that that's how the rich get richer, and the rest of us pay rent, right? Okay. Um, anyway, so the Y value is in this exponential formula. You start again with a starting value times. You see this little dot here, times. Okay. Times means it's exponential growth. This is not a plus or a minus. If it was plus or a minus and it was the same number, it would be linear, like we just saw on the previous slides. So when it's times, okay, you take the multiplier, okay, whether we're multiplying by 3 each time or 5 each time, or in investments, 20% each year, 0.20 each time, to the, you see this exponent, this is the exponent is the independent variable. Let me show you what I mean. Like, we were just talking about apartment complexes and how many years it's going to take them to make a profit. Okay. Well, let me look over here, my example on the left here. So year one here. Okay. All right. Year two here. They're all years. All right. Now you can see, if I mean, just looking at my illustration here, you can see at about year 3 and 4, you really start to make more profit, right? That's why in exponential growth, that X right up here, that's your, like we said about a half hour ago, 3 to the third, okay? That's the exponent. That X is which year it is. So if it was the 5th year, for instance, it would be the multiplier to the 5th, okay? So it would be the starting value, okay, times the multiplier, whether it's 3 or 20% or whatever, that multiplier to the 5th power, if it was the 5th year, independent variable 5. If it was the 6th year, independent variable 6, okay? Now I'm going to tell you a little trick here now. Hopefully I've given you enough time to kind of copy what's on this slide here. I want to talk about your calculator on my next slide. I said I was going to get to this here. So I want you to look over here first at what I'm looking at, showing you on the far right-hand side here. On your calculator, your TI-30XS, on the it's on the left-hand side, on the far left-hand side. Okay, if you looked in the left-hand row here, okay, you'll see a little thing that looks just like this. What I have in the box here, it looks like an x squared. Okay, if you're squaring a number like 2 squared, you would put in your calculator 2, and then you could press that x squared button and it will square the number. Or if you had, let's say, 19 squared, okay, and you didn't want to try to figure all that out, you could press 19 and then that little button that's on the far left side of your calculator that looks like this, x squared, you could press 19 and then x squared and it'll square it. So that is the little thing here. Here's your little key on your calculator for squaring numbers. It's only for squaring numbers, which means 19 times 19 or 2 times 2. Now, but what do you do if they're talking about this exponent? I'm circling on the screen here. There's 4 here, okay? to the fourth power, okay, how do you do that? Okay, right underneath that key right here, this one that looks like this on your calculator, right, is it, no, it's right above it, excuse me, right above it is a key that looks like this one right here. It's right above the squared key, okay? And so if I wanted to do 2 to the third, for instance, here's what I would do. I would press 2 on my calculator, press that little arrow key that's right above the squared key. And again, it's on the left-hand column of your calculator. It looks like a little up arrow. And then I would put 3 in and press enter. And that would cube, that's 2 to the third. If I had 19 to the third or 19 to the fifth, for instance, okay. See how complicated that would be to calculate that out? I would press 19 on my calculator. I would press this little symbol here, okay? And then I would press 5, and then I would press equal, and that would get me 19 times 19 times 19 times 19 times 19, 19 to the fifth, which by the way, would be a huge number, okay? Now, why is that important for you right now? Because when you do your homework, you might have to figure out to the, see how I've got days in my chart here? What if they wanted to know the 12th day or the 50th day? And so it would be to the 50th. Without that little magical key right here, I'm going to draw an arrow here. Without this little magic key here, it'd be really hard to figure it out. But with that key on my calculator, with that button, life is much easier. Okay. Okay, so that's how you'd do exponents on a calculator. In my chart here, let's say I was trying to figure out the fourth day of my growth, how much money I would have here. Okay, number of people infected by that day. So on day 0, before I started counting, there's 100 people that were infected with COVID-19, let's say in Washington State or in Snohomish County. Okay, and then on day 2, there's 200. And then, I'm sorry, on day 1 of me counting, there's 200. Okay. On this, after the second day of counting, there's 400. So third day, there's 800. It looks like we're multiplying times 2 each time. That is my multiplier. Okay. 400 times 2 is 800. 800 times 2 is 1600. 16 times 2 is, there's my multiplier. Okay. All right. I can figure out, let's say if they ask for the fourth day, how many people are going to be infected with COVID-19. All right. You could figure that's my Y value. Okay. That's my dependent variable. Okay. That's my number on the Y axis. You can figure out after how many days. At the fourth day, you would start with your starting value. That's 100. I started with 100 people that had COVID. Okay. All right. Times the multiplier, which we determined was 2, to the fourth power. That's my exponent because we're asking for the fourth day. On our previous slide, it was to the x value, okay? And that would give me my, how many people would be infected on the fourth day, okay, 4 days out. All right, that was a mouthful. Hey, I did it, only went over 10 minutes over time. I thought it was going to be a half hour overtime. Now I want to stop here and make a couple announcements and try to calm you down because some of you right now are going, man, there was a lot of stuff and it got arithmetic and geometric and now exponential and linear. How am I going to remember all that? Here's how. You're going to have your notes, both for your homework and for the exam 3. Additionally, to make life sweet for you, next Tuesday night, even though technically the quarter is supposed to be over and we're really supposed to be just doing finals, on Tuesday night of next week, I will use this class time to go over the whole third exam, just like I've done for you the previous 2. So don't panic. You're going to have, I will send to you the practice exam 3. It'll have the answers on it. Next Tuesday night, we'll go through, there's only 20 questions on the third exam. We'll go over each type of question. You'll have that sheet of paper with all the notes. I guess I can turn my face back on here. You'll have that sheet of paper with all the notes. And let's share my video. And I think I'm going to stop the recording.